Hello everyone, this is Sachin Grover. Thank you for checking our demonstration on natural language understanding for embodied planning agents using LLMs. This work was done in collaboration with Shivali Mohan at SRI. Before checking the demo, let's first look at the overview of the system and get some construction details to understand the demo. We use AI2Thor simulator to show a functioning embodied agent. It interacts with the user using LLM as an interface for natural language understanding of the task requested by the user. This is the diagram showing the complete system. It is divided into three parts. Red part on the left performs linguistic reasoning on the request from the user and converts it to intent semantic representation called ISR. The ISR is grounded using real-world objects and is converted to goal predicates in grounded reasoner shown by the middle blue region. This, with the robot's capabilities and the current state description, is converted to a planning task and sent to a planner to generate a plan. The plan is executed in the AI2Thor environment. Now, let's look at each of these parts more closely. We use web-based interface where a user can type their request. For example, in this case, they have added put bread in fridge. This request is converted to intent semantic representation or ISR, that is a JSON describing different objects and the intent of the user. For example, in this request, there are two objects, bread and fridge, with the in relationship between them. The ISR is converted to PDDL predicates showing real object IDs. Internally, we map these IDs of objects in AI2Thor with simpler IDs in the system to decrease planning errors. Where fridge ID in AI2Thor is very complex, we convert it to fridge 0 in the system. Domain of the environment is constructed using robots' capabilities. On the left, you can see the PDDL description of actions teleport, pick up, put and open fridge. The goal condition received from the grounder with the current state description is used to construct the planning problem shown on the right. In general, there can be over thousands of predicates to define the current state of the objects in the environment. We create partially grounded actions to remove infeasible actions such as pick up fridge. This also helps with the combinatorial complexity of grounding every action for every object in the environment. Any state-of-the-art planner can be used to construct the plan. We used FF with a simple heuristic and the plan was constructed in less than a second. We had also tried one of our internal PDDL plus planner called Nix. It uses BFS and even that without any heuristic was able to generate the plan in few seconds. In this case, the plan generated is teleport to bread's location, pick up bread, teleport to fridge's location, open fridge, put the bread inside the fridge, and close fridge. This is the AI2Thor simulator. On left, you can see the first-person view of the Thor agent, and on the right, you can see the top view of the kitchen area. In the top view, you can see AI2Thor agent standing in the center of the kitchen. All these modules communicate through request over open HTTP ports in Python. Let's start each of these modules. First, we start the AI2 simulator. Then the agent, and finally the NLU interface for user to type the request. User adds the command keep bread in fridge. On right side in the prompt, you can see the plan being generated. Then the plan is executed in the AI2Thor environment on the left. Next command this user types is, can you put spatula in the drawer? Again, the plan is generated on the right and executed on the left. In the third example, robot is asked to put the mug on sink basin for cleaning. As one can notice, the language has become more complex. However, our system, with the help of an LLM, is able to handle the complexity. For the last demonstration, user asks, would it be possible to put apple in the fridge as well? As you can see in the execution, that bread is still in the fridge, essentially showing that we are continuing in the same environment. This concludes our demo. Thank you for stopping by.